Hi everyone, welcome to this online masterclass on managing the microclimates. My name is Femke and I'm working at MetaMeta as a program manager microclimate. And together with my colleague Sean, who is a program manager in regenerative agriculture, we organized this online masterclass. And this is part of a Green Future Farming project, together with our partners, Just Dig It, Aid Environment and Rain. And we also invited IDIWatch to join this masterclass and tell something about their expertise. So before we start, I would like to highlight that this masterclass is supposed to be interactive. So we really want to raise this open discussion. So just for you to know, to feel free to share any experiences, thoughts, or questions during the presentation. So it would be nice if everyone mutes themselves while someone else is talking, but other than that, feel free to unmute yourself at any time and take the floor if you want. So the session that we organized is lasts from now till 5, so 3 hours in total. And we divided this up in 3 different sessions. So I will start with providing an introduction on microclimate management. So why the microclimate and why we as MetaMeta see so much potential in this concept. So I will shortly elaborate on what is the microclimate. I will show some practical examples of microclimate management and tell you a little bit more how this microclimate system works. Then in the second session, my colleague Sean will tell you more about all the microclimate management practices. So this ranges from water collection and conservation practices to managing the wind. But Sean will tell you all about that in an hour. And then in the last session, we will discuss our way of working towards a microclimate management tool. So we'll talk about the prototype decision tree that we created to manage the microclimates. We'll talk about monitoring and mapping the microclimates. And this is also where our partner IDIWatch will join the stage and tell you more about their tools and their ways of working. So we'll start with the first session on the introduction to microclimate management. So first of all, why the microclimate? Well, I think we're all very familiar with the increased climate change threats as a result of global climate change. We all know that the global temperature is rising, weather patterns are becoming more irregular, there will be more extremes already happening, but also even more in the future, consisting of heat and cold waves. And unfortunately, automatically, this leads to ecosystem degradation. And as crop production is highly dependent on good climatic conditions, this can also result in agricultural yield gaps. And this, of course, highlights then the importance of first building climate change resilience, and then, of course, as well, increasing the agricultural productivity. And a solution that we think can be really helpful in this aspect is then microclimate management, as the microclimate buffers against global climate change, and therefore it can improve the agricultural production conditions. And this is then the result of better germination, better moisture levels, and more moderate air and soil temperatures. And how the microclimate can then buffer against global climate change is explained here in a nutshell. So the good microclimate management can actually increase the water retention on a very local scale. This then reduces the local temperatures, and this combined will then increase the local ecosystem resilience, which will then provide a buffer against global climate change. Well, how this works and how this can be done in more detail will be explained during this masterclass. So research, which will be elaborated on later on more, showed that good microclimate management has actually the potential to locally lower the temperatures by 1.5 to 2 degrees Celsius. So this actually shows that microclimate can serve as a buffer against the predicted 1.5 degrees in global temperature rise. And this is why we really see microclimate management as a third way in dealing with climate change next to climate adaptation and climate change mitigation. And we also really see the potential of microclimate management, as this is very highly accessible and can be done on a super local scale. Yeah, and then the power of the microclimate actually lies in the high variability on the small scale. So on a higher atmospheric level, more mixing processes are active, which is why the mesoclimate and the macroclimate are actually more moderate and more stable. So there's not much variability in that. And unlike the microclimate, which is which is highly variable, this actually brings the climate back to more manageable levels. So it's almost impossible for humans to actually change the global climate, but the microclimate, on the other hand, can be changed by making changes in the landscape. So this really shows the opportunity for people to change and improve their immediate environment. But then how can the microclimate be managed? Well, changes in the landscape actually lead to changes in the surrounding microclimate. So this also shows that improving the microclimate can be done intentionally through land and water management practices. Unfortunately, this opportunity is currently overlooked, and microclimates are usually an unintended byproduct of other interventions. So there's mostly a lack of consideration and predicting larger climate change trends, long-term rainfall patterns, and temperature averages are way more the norm. And yeah, we really think this is a missed opportunity. An example of how not taking the microclimate into account can be found in Nepal in this road construction project. So the constructions of the roads in the Nepalese mountain environment actually led to openings in the very steep mountain terrain. And this increased the exposure to sunlight, to wind, and it's also changed the runoff patterns, ultimately leading to drying out of the area. And this really shows the importance to take the effect of landscape alterations on the microclimate into account. So here changes were made into the landscape, which changed the microclimate. And in this case, unfortunately, it changed it for the worse. So it's really important to, before such changes are made, to take the microclimate into account and make sure that the microclimate stays either the same or positive. So for example, in this example, a solution could be to implement practices that retain the moisture and regreen the area next to the roads by, for example, using the rocks and boulders that are becoming available during the road construction. Then, before I continue talking, I'm really curious if you had any experiences when a change in landscape led to a different or even worse microclimate. So feel free to take the floor and share any experiences that you might have. Or share in the chat, that's also possible, of course.
Maybe people are still a little bit shy.
Yeah, probably. Yeah, we can also continue. I think we have a lot of other options to discuss. Yeah, so why the microclimate? Well, focusing on the microclimate can thus uncover methods to increase the resilience of the landscape. And this can thus buffer against the climate extremes as a result of global climate change. And as a result, this then increases the agricultural productivity. But to do this more systematically really requires understanding of the microclimatic system and its impact in the field and on crop production. And therefore, the aim of this first session is to give an overview of the system and how this works so that interventions can be done to the system. So then what is the microclimate? Well, the microclimate basically is where meteorology lands on Earth, and a very fancy definition of this is given by Vokan in 2008, and he said that the microclimates are the localized dynamic interplays between different processes in the surface layer, such as energy and matter exchange, radiation processes, and the effect of the underlying surface. And then microclimates are the result from multiple climatic components. which are all listed here. So this is solar radiation, air temperature, soil moisture, soil temperature, air humidity, and the wind direction and speed. And the microclimates are then determined by specific landscape, soil conditions, vegetation, land use, and water retention. So that can all be seen in the middle circle here. So all these different aspects actually then influence the microclimatic components. And so this means that the high variability of landscape then also results in a variable patchwork of different microclimates spread over areas. So for example, if you're on the lee side of a mountain in a tree shaded area, you have a completely different microclimate than if you're on the other side of the mountain in the full sun with less trees. So this really shows that this high variability in the landscape then also results in very different microclimates. And an example of this high variability of the microclimate is given here by IdiWatch, and this is an agricultural plot in California. And this shows the soil temperature on a 10-meter scale. So you can really see that for parts that have a higher soil moisture level, they have also lower soil temperature. So this really shows that even though this plot might seem very small on like a global scale, you still see a lot of variability within this plot. Another example is, for example, this quarry in Italy. And this is then an example that is created by nature itself. So this quarry actually created a special microclimate than the rest of the landscape. So within this quarry, it's way cooler, more moisture, and it's protected from winds. So this really shows that a change in landscape also leads to a change in the microclimate. And then this is actually where the power of microclimate also lies, because this high variability of microclimates can then be used to make the right interventions in the landscape to improve the microclimate. So these are some practical examples. So for example, we have this French vineyard where they used stone cover. So this whole vineyard is covered with stones, and these stones actually regulate the temperature. And they also retain the heat within the soil at night, which is very useful for frost prevention. So they actually raise the heat at night on a very local scale. And then the stones also prevent the evaporation of moisture from the soils, and then result in enhanced soil moisture levels, which also moderate the temperature. So this really shows that doing one interventions on a site, in this case adding stones to the terroir, can actually then change that local microclimate. Another example can be found in the Andes, where farmers have this very inventive system of raising the fields, which are called varus, and then in between the raised fields the water is retained. So this actually creates these water bodies, and the water then acts as a buffer against the night frost, because the heat is stored during the day and released during the night by the water. So this actually research showed that on these raised beds, the nighttime temperatures may be several degrees higher than on the rest of the field that doesn't have these water bodies. So this also shows that making a change in the landscape, in this case, raising the fields and adding water bodies to it, really changes the local temperatures, which in this case is used for crop production as well. So now again, I'm really curious about your experiences. So maybe I know that some of you are actually working in land and water conservation projects, or maybe even on the field itself as a farmer or agricultural worker. So I'm really curious if you are doing anything on the land that changes the microclimate of that land. And do you do this intentionally, or now you think about it, this actually happened unintentionally? So feel free to unmute yourself and or
they can raise their hand.
Yeah, you see me, Femke?
Yeah.
Hi.
Hi.
It's Francisco here. Hey, no, nice to be here. Now, just want to share a couple of things. So, one thing, I started a small farm in Spain the past spring, 2021, and this very, very hot in summer. I don't know if you're presenting this later on, but so what we are doing is trying to lower the temperature for our horticulture production, specifically for lettuce salad. So we use some shade nets, so they shield 50% of the incoming solar energy off. So we are seeing a decrease in the middle of the day of about 10 Celsius degrees. So that's one thing that that I wanted to share, and is quite effective. Still, we are struggling because lettuce is not the best of summer crops, but that's one thing we are trying.
Nice. Yeah, I think it's really cool that even though the climate might not work for your crops, that you can do things yourself on your garden to really change the microclimates.
We are trying, but we will try to improve it further. So I think also how you play with water has a great influence, but I'm sure you will explain a bit of the dynamics of water in the soil later on, right?
Yeah, for sure.
Yeah. Great.
I also have one example that I can think of, and I think also Francesco can back me up here. I work for Just Dig It, and we have quite a large-scale reforestation, agroforestry reforestation program happening in Tanzania, in the Dodoma region. And I was there back in 2018, quite a while ago. And then we visited some villages for a baseline. And I remember that the way I remember is that Dodoma is quite a hot and a dry area. Well, we arrived in this one village called Bumila, and a few years before our program started, there was another program also focused on the same techniques. And I think it was a program about World Vision. So there were already a lot of trees regenerated there, and I remember that the village felt so different compared to all the neighboring villages. It really was a huge difference. It felt cooler. It felt more pleasant just being there. Obviously much greener. So I think that was a good inspiration for our program that we could work towards. Actually, it's not something I haven't been there since in our program area, so I don't know what our current situation is. And it's not something that's included in our monitoring approach yet, but I'm very curious to learn how we can do that. But yeah, I thought it was a nice case to share.
Yeah, very beautiful story. It's really nice that I showed the map of Watch that's created by remote sensing, but it's also really nice to hear that by actually walking through the village, you can feel as a person already like the changes. So yeah, thanks for sharing. Really, really nice story.
Yeah, thanks.
Yeah, so then we'll move forward to talking more about the system itself, so the microclimate. So I showed this beautiful infographic made by Madia before already. And we now know that it's possible to actually change and improve the microclimate. But to do this more consistently and systematically, this requires very good understanding of the microclimatic system. And this understanding then provides the building blocks for understanding how different land and water management practices can then actually transform the microclimate. So we'll talk more about these practices in the second session, so in half an hour or so. But I will first elaborate a bit more on how the system works. So we'll start with solar radiation. And solar radiation is basically the driver of all microclimatic processes, as the sun is the primary source of all energy. And the conversion of this solar radiation energy into heating of the air and soil is actually what creates the local microclimatic system. So if we want to know how the microclimate works, we should definitely start with solar radiation. yeah, so all energy coming from the sun is actually shortwave radiation, and not everything is directly received by the Earth. So some is first scattered by clouds or other particles in the air. And some is also directly reflected by the Earth itself. And the proportion of solar radiation that is reflected into the sky as diffusive solar radiation is then called the albedo. The Earth itself also radiates, it's also radiating as it contains heat, and this is called long wave radiation. So this is important to take into account when we start talking about this energy balance system. So the concept of albedo is actually that when a surface is not entirely white, a part of the solar energy is absorbed. So for example, as you can see on this scale, water surfaces have a very low albedo, and this is why they serve as a very good sink for solar energy, as we saw in the examples from the water bodies used in the Andes. And then the amount of solar radiation that is received by a site depends upon the Lawbert-Cosin law. And just to save you from a very long explanation, this is basically the sun's position compared to the Earth. So when the sun is at the highest point, this means that radiation is at maximum. And on a site, so in the landscape itself, there are actually two factors that influence this. So first is the aspect, so that's the compass direction, so what way you're facing on the site, and of course the slope. And as the aspect and slope then also determine how much solar radiation is received on a very local scale, this makes the aspect and slope also very important for the formation of the microclimate. So it's good to take these aspects into account, because later on we'll show that you can actually tweak these aspects into like changing your microclimate. So then what happens after the solar radiation is received by a system? Well, all energy fluxes that go within a system actually must balance. So this means that the solar radiation that comes in either contributes to latent heat flux or sensible heat flux. And latent heat flux consists of evapotranspiration, and sensible heat flux is the heating of the air and soil. So how this then works out in creating different ecological systems is shown in this picture. So on the left side, we can see a very desert area, so where there's low soil moisture. And this means that less energy will be going into evaporation fluxes because there's no soil moisture available to evaporate, basically. So this means that more energy has to go to the sensible heat fluxes, meaning that a lot of energy from the soil then contributes to rising up the soil and the air temperature. And then on the left-hand side, we see a more vegetative area where there's more soil moisture as well. And this means that evaporation and evapotranspiration is actually possible. So this means that more solar energy will then go to these processes of evapotranspiration. And this means that then less energy will be available to heat up the air and the soil. So as a result, the system on the left, as you can see by the, how's the thing called again? I forgot the name, but the temperature on the left turns out to be way higher than the temperature of the ecosystem on the right. So this division of solar energy going in either the latent heat flux or the sensible heat flux is very important when looking at microclimates. So to conclude, the solar radiation is the driver of how the microclimate is formed, and then there are several aspects that can influence this. So we saw the albedo, we saw the slope and the aspect of the surface, and the distribution of solar radiation into latent or sensible heat fluxes. And this then, as we saw from the previous example, depends on the availability of soil moisture and vegetation. So then the soil moisture, as we also saw from the previous example, soil moisture is a very important determinant for the microclimate. So whether or not soil moisture is available will tell a lot about the microclimates that is happening there. Soil moisture is basically the volumetric measure of water per cubic meter in the soil. And as can be seen from this picture, the water content in any soil layer can actually decrease by soil evaporation, root absorption, or flow to an adjacent soil layer. So the amount of soil moisture that is within the soil is constantly changing. And the amount of soil moisture available in the soil is actually determined by the soil's water storage capacity. And this storage water capacity is determined by the texture, the structure, the depth, the organic matter, and the biological activity of a soil. And then the texture of the soil is determined by the relative amount of clay, silt, and sand particles. So the smaller a particle, the higher the potential to absorb water. So actually clay has super small particles, so they have a high potential to absorb water compared to, for example, sand. And unfortunately, this textural class of a soil cannot be changed easily. So this is also not really something that people can easily change on their land to increase the soil moisture capacity. But the soil organic matter, on the other hand, and the structure are things that can be influenced. And as these also helps to increase the soil water retaining capacity, it's very important to take this into account. So this figure actually shows that the more organic matter in the soil, the better its water holding capacity. So we saw that soil moisture levels, of course, should not be too low, but they should also definitely not be too high, because too high soil moisture levels can actually result in a lack of oxygen supply, meaning that there is no air available for the soil microbes. And this then makes the process of respiration impossible. And soil respiration is basically the breathing of the soil. So this is where the CO2 comes out of the soil again. So it's very important to balance the soil moisture, so not have too little, not have too much. And this figure actually shows that optimal conditions for microorganisms in the soil to break down the organic matter and thereby release nutrients and fix nitrogen. For this, it's important to have a soil moisture content of around 60% of the open water pore space. Yeah, and as we saw before, soil moisture is a very critical microclimate determinant because it plays a huge role in the division of energy into the sensible heat flux and the latent heat flux. So soil moisture is needed for evapotranspiration. So when there's sufficient soil moisture, evapotranspiration is possible, meaning that more energy will go to the latent heat flux. And the more energy will go to the latent heat flux, the less energy will remain available for the sensible heat flux. So this means that when there's sufficient soil moisture available, the near surface air temperature will be lowered. So this actually shows the role of soil moisture in forming the microclimate and actually the availability of soil moisture to then also balance this microclimate. Next to the amounts of soil moisture, it's very important to also consider the movement of soil moisture through the soil to ensure that soil moisture remains available at the subsurface. So the process that enables this is called capillary action. So when there's a deficit of soil moisture at the top, so for example, because of crop uptake, so through transpiration or evaporation, this actually creates a deficit of soil moisture at the top. And then the capillary action makes sure that the ground table rise up to make sure that remains enough soil moisture in the top. But the speed at which this happens really depends on the soil structure. For example, a sandy soil, which has a very coarse structure, meaning that the like the grains are very well compared to, for example, clay. They are very big, so there is also a lot of pore space, meaning that the water can move very quick. But on the other hand, the capillary action is a process that takes place against gravity. So that means that too big pore space can also actually then make sure that the water can't move that fast. So in that sense, a more fine soil texture, such as clay, enables way more capillary rise than a sandy soil, but it's slower. So that's something to take into account. The movement of soil moisture also depends on the temperature gradient. So basically, soil moisture also always moves from more warm to cooler places in the soil. And this whole process of capillary rise actually makes rain-fed farming systems way more reliable. So therefore, it's very important to take this into account. As after a rainy period, soil pores then transport the water back upward because of the capillary action. And this then ensures the water availability after the rainy season has ended. Then the third one, soil temperature. Soil temperature is actually determined by the incoming radiation, as we saw before. So a factor in this is actually, for example, is there vegetation on the site that serves as a reflector or an absorber of the incoming radiation, or basically any other structure on the site. So only the radiation that actually is received by the soil then contributes to a rise in soil temperature. Another aspect that can influence this is the soil color, as we saw before. This is called the albedo. So the darker the soil, the lower the albedo, and the more the soil temperature will rise. Another aspect that's important is thermal conductivity. So a higher thermal conductivity actually means that the radiation flows in and out at a faster rate. So for example, water has a very high thermal conductivity. So this means that the presence of water dramatically increases the thermal conductivity and then makes soils cool down way quicker. So this shows that soil temperature extremes will also be modified when the soil moisture content in the soil is sufficient. So this is very important to take into account when looking at microclimates. Then soil temperature is also a very important factor in crop production, of course, as this provides the warmth necessary for seeds, so for germination. It plays a role in plant root development and in the work of microorganisms. So as this picture shows, it's very important to moderate the extremes, as too low soil moisture will stop plant root development, but also too high soil temperature will put a strain on the development of roots. So it's very important to actually balance this. Soil temperature is also very important for biological processes of microorganisms. And again, here, this figure shows that too high soil temperatures can actually stall the biological processes of microorganisms, but also too low temperatures actually inhibit the water uptake and nitrification, and that then also leads to a reduced soil fertility. So again, this really highlights the importance to moderate the extremes and to buffer the microclimates. Then we move to air temperature. So the local air temperature is a result of incoming and outgoing solar radiation. And as we saw before, the sensible heat fluxes increase the air temperature. And there are several on-site modifications that then affect the air temperature. So this, again, comes all down to the division of the sensible and the latent heat flux again, as vegetation can actually increase the transpiration and lower the local air temperature. And moisture in the soil can also decrease the local air temperature by enhancing evapotranspiration. Air temperature is also very important for crop production, as this is highly determinant for the photosynthesis rate. So this figure actually shows that an optimal photosynthesis range tends to be between 20 and 30 degrees Celsius. And this then makes the air temperature very important for aquaculture. Then the fifth aspect of the microclimate, air humidity. So air humidity results from evapotranspiration, and it's the amount of water vapor in the air, which is then the basis for cloud, fog, and dew formation. And the most used parameter to indicate air humidity is the relative humidity. And a relative humidity of 25% then indicates that the air is holding 25% of the total water vapor that it could hold. So this means that a relative humidity of 100% means that the air is saturated, and then mist, fog, and clouds will form. And an important aspect in this is the air temperature, as the air temperature determines the amount of water vapor that air can hold, with warm air being able to hold way more water than cold air. So this can also be seen in this picture, that at the same amount of water vapor, the relative humidity at a system of 30 degrees is way lower than a system of 10 degrees Celsius. So as I said before, when the air is saturated, so this means a relative humidity of 100%, mist, dew, and fog and clouds can form. So for example, dew will form when the moist air contacts a cooler object. So then the air becomes too cold to carry the moisture, and then dew will form. And the temperature point at which this happens is called the dew point temperature. Yeah, and this dew and fog formation are actually very essential for plant growth, as they can be essential moisture sources. And dew is also important in the pathology of fungus diseases. So here's this one example from Yemen, where there is a valley blanketed with stones and trees so that the dew can form, which then contributes to soil moisture. So the stones really cool off. And then when the air that holds the water touches this, the air temperature drops, and then the dew will form. And in this system, this turned out to be a very important soil moisture source. There's this other example of Italy, where these stone walls or fragments of stones were created in the field. And then when these stones cool off strongly, they draw the moisture from the air. And when this then touches the stones and goes below dew point temperature, then the moisture will contribute to the system itself. So these were two examples, but very curious if you have any examples of using dew as a moisture source yourself, or this is not something that's really common. For example, we heard some stories from farmers in Ethiopia that intentionally leave the stones on their side to make sure that this captures more moisture. So if no one does this or has an experience, we'll just move on. So I showed some examples of dew formation, but of course this can also be done for fog. So this is actually an example from Peru, where they put artificial fog collectors consisting of a metal frame covered with mesh that actually replicate the effect of leaf surfaces. So when the air goes through this mesh, then the fog is captured, and then this contributes to the local water balance. So both these examples actually show that both fog and dew play a vital role in forming the microclimate. And this is then not only in terms of increasing the soil moisture, but also because the dew formation on soil actually darkens the soil. So this then impacts the albedo rate and the air movement. So because damp air is less dense than dry air. So this affects how the air is moving on a very local scale. And of course, fog and dew both play an essential role in the formation of precipitation. Then we'll move to the last aspect of the microclimate, which is the wind direction and the speed. So as can be seen from this picture, winds are the results of differences in pressure fields. So winds always move from high pressure to low pressure. Yeah, and when the wind is then parallel to the ground surface, the flow is said to be laminar. But on a small scale, this never happens because there's a lot of turbulence that is generated by roughness of the surface. So the heterogeneous surfaces of landscapes can then result in a very complicated wind flow system. So there are a lot of eddies that will be formed by, for example, a tree in a field or a house or whatever structure there is on the site. Winds play an essential role in understanding the processes of heat transfer and, again, evapotranspiration, as winds wipe out the boundary layer of soil and crop leaves. So this is also called the clothesline effect. And by doing so, they remove the constraint on evapotranspiration. So this way, wind can actually then enhance the evaporation of soil moisture and both the transpiration from leaves. So both these processes actually increase with the increase of wind velocity. And this can, in terms of crop production, result in impaired plant water status because, for example, if the wind is too fast or too strong, the transpiration process happens too fast. And if there's not sufficient soil moisture available in the soil, this can then result in low water uptake by the plant. But it can also enhance crop production since it also cools off the plant and removes the excess humidity, thereby also reducing the potential for pests and disease. At super high wind speeds, winds can also have mechanical effects in terms of crop production. Winds can transport dust, sea spray, pathogens, predators, and air pollutants. And unfortunately, wind can also result in soil erosion and therefore reduce soil fertility. And this then results in a loss of vegetation potential and lower soil moisture holding capacity. So this really shows that when managing the wind, you should really look at the site and see if it's actually harmful, yes or no. And if it's harmful, there are many ways to actually change the direction of the wind or to lower the wind speed. We will talk about this later on. Yeah, so we talked about huge picture. We talked about all the 6 microclimates components, which are here in the green boxes. But of course, these components are not standing by themselves, and the microclimate really works as a system. Yeah, so we talked about all the different processes, factors in the white and the gray boxes. And then actually this picture shows that all processes actually relate to each other. Yeah, so when doing something to a microclimate, you should really think of it as a system instead of just altering the wind direction or the speed, because this really has an effect on all the other components as well. Yeah, so this system perspective when it comes to microclimate management is very important. Yeah, so then again, we're almost done with this first session, but before we end, I'm very curious if you have any thoughts on the microclimate system so far, or what are the biggest climatic challenges that you experience? Yeah, and then more importantly, how does this then translate to the local microclimate in which you operate? And again, feel free to say it in the chat or to unmute yourself to say it out loud in the group.
Yeah, maybe if you mute yourself, I can unmute.
Yeah.
Yeah. Hi, everyone. Thinking to, yeah, exactly. Yeah, so I was just thinking about the fog catching example that you gave, and it reminded me of a system that I saw on the island of Madeira, actually. So So it's a volcanic island, so they have really tall peaks, but it's all plateaus at the top. And it's also quite a water scarce island. So what they did was they planted a lot of euphorbia species, which is native to the area and really efficient at harvesting fog. So as soon as the fog touches this euphorbia, it all condenses. But then to bring that where they needed it, the bottom where all the agriculture is, they had these channels just dug out along the contour of the hillside, and yeah, the euphorbia is basically channeled all that fog down into the channels, and then by the time you get to the bottom of the hill, you've got a really constant flow of water all year round. So it just shows how much water you can actually store in the air, and it's a resource that a lot of people aren't thinking about today. So yeah, it's nice to highlight this, and that is actually an option in places where you might not consider it. Yeah.
Yeah, thanks, Sean. Very cool example. Maybe anyone else who has a similar experience or?
Yes, Femke, Francesco again. Well, it's actually quite similar to the one of Jean, but in the Azores Islands in Portugal, where they are doing grapes quite close to the coast, and it would be very difficult without this measure because there is very strong ocean winds. So what they did is build a lot of small walls. It looks like a labyrinth, and they grow grapes within the labyrinth. So there is less sea spray, the wind speed is reduced, and with all the effects I can imagine it can have on evapotranspiration and all processes we just spoke about.
Yeah, we actually included a very pretty picture of this, but this will come in the next session. But yeah, it's
okay.
Yeah.
Spoiler.
Yeah,
okay.
just for everyone else, there will be a picture coming soon. Yeah, nice. I think if no one else wants to take the floor, I think it's good to take a 10-minute break.